Hi, today we're going to talk about some important properties that context-free grammars might have, and also one special form of context-free grammar called the Backus Naur Form. All I need you to remember for this is what a context-free grammar is and how they work. What we're going to be particularly talking about is the most important aspect, the rule systems. So the first important property is recursion. So you know that when we talk about a programming language having a recursive method, it means that the method ends up calling itself. So we end up in some cycle where something is referring back to itself over and over again. And that's what recursive means. So a rule is recursive, basically, if we can expand the non-terminal on the left through some path through the grammar and eventually get back to that same non-terminal. So the more formal way to write this is that a rule is recursive if and only if it is written in the form here, where we expand the non-terminal into something with another non-terminal in the middle, where these two W1 and W2 may be part of the entire terminal non-terminal alphabet, and where this Y non-terminal can eventually, and that's what this means here, can eventually be expanded back out into something that contains X again. So basically, if there is some way for us to follow the rules where we eventually replace X with itself. So we can straight away see here that something that satisfies this recursive rule is simply X going to X. Or, as we had before with our balanced palindromes language, one of the rules, S goes to S surrounded by something, fits the rule, the definition for recursive. We call a grammar recursive if it contains at least one recursive rule, and so obviously any grammar that has no recursive rules we don't call recursive. So another property that we care about is the property of a grammar or a rule being self-embedding. So this is a special case of the recursive rules. So every self-embedding rule will also satisfy the requirements for being recursive. So we have the same format again, where we've got rules are self-embedding if we can have a non-terminal expand out into something that contains another non-terminal, where that non-terminal can eventually become something that contains the original non-terminal. But in this case, we've got a slightly stricter condition. The concatenation of the first parts, W1 and W3, so everything that eventually ends up out the front of the X, has to be a member of the input alphabet clean plus. So it can't be empty, and it doesn't contain non-terminals. Whereas before we were looking at, with the recursive rules, we were looking at all possible symbols cleaned. And again, the bit that goes at the end, W2 and W4, concatenated, has to be a non-empty string made up of input symbols. So what a self-embedding rule eventually does is turn X into something where we have a string followed by X followed by another string. So where the rule embeds itself into terminal symbols. Just like with the recursive rules, a grammar is self-embedding if it contains at least one self-embedding rule, and a grammar which has no self-embedding rules obviously isn't self-embedding. Self-embedding is a slightly more useful property for us for grammars, because with the self-embedding grammars we can describe languages like the balanced parentheses language, or ANBN, or anything that has the form where we have some fixed strings, UX and Z, and then we have some other strings here which both have the same repetitions of maybe some other parts of strings. This will be useful later when we talk about a way in which we can prove that certain languages cannot be expressed with a context-free grammar. So just some quick examples. A grammar with a rule in this form is clearly self-embedding because we go from a non-terminal back into something that contains that same non-terminal, but where we have a non-empty string of terminal characters out either side of it. This rule here is a recursive rule because we eventually get back to the same non-terminal again, but we don't have a non-empty set of terminal symbols on the right-hand side of the resulting expansion, so this is not self-embedding. This rule here, the individual, the first rule here, whilst it doesn't look as obviously self-embedding as the first one, when we eventually follow it out to include this rule here, we see that it is self-embedding because we've got W1 equals A and W2 equals EPS, but W3 equals EPS and W4 equals A. So when we concatenate W2 and W4 and W1 and W3, so if you go back to the definition of self-embedding, you'll see that in this case we've got W1, W3 is A and W2, W4 is A. So that fits the definition we had for self-embedding. And we can see that because we eventually end up with something, if we look at the parse tree, where we have inserted S back inside of something that contains some input alphabet strings. So we've inserted S back inside of a non-empty string. Now, one important consequence of the property of self-embedding grammars is the following. If we have a grammar and that grammar contains no self-embedding rules, then it generates a language which is regular. So this statement here implies that the language is regular. Now, the negation of this, i.e. G is self-embedding, does not imply the negation of this here. So we can have a rule where we have a regular language, but we have a grammar which is self-embedding. As you can see by this example here, this describes a regular language because it's a grammar built up, a context-free grammar built up of only one symbol. If a language has the property that every grammar that defines it is self-embedding, then we know that the language is not regular. So if there's no way for us to build a grammar where we don't have to have at least one self-embedding rule, then that language is not regular. And we can see that that follows from the first statement here. Alright, so we've looked at some properties of grammars. Now we're going to look at a special form of grammar where we represent things slightly differently than the way we have in this course, and that is called the Backus Naur Form. Now this form is often used to describe programming languages or communication protocols or things like that. So some of you who have taken some internet communications courses in your first year, or maybe some of you who have looked into teaching yourself programming languages may have stumbled across Backus Naur Form. So the basic version has its non-symbols as something surrounded by angle brackets. And it often uses the pipe symbol in the same way that we have in this course to be read as OR. So if we have a rule, so in this course normally if we have a rule, say S goes to A and S goes to B, we often simplify that down into a single rule, S goes to A or B. The same thing happens in Backus Naur Form. Also, often the symbol : equals is used where we use the right arrow. So an example of a Backus Naur Form for a language which we might have, for a grammar which we might have written as S goes to A, S, B, goes to S, S, and goes to EPS is written like this, where we replace the capital S as a non-terminal with the word start in angle brackets. Now here's a sample of some of the Backus Naur Form that describes the C programming language. Now this is a very small sample of it, but you'll notice that if you go and look at look for B and F for various programming languages, you'll find often that they're not as long as you might expect them for something as powerful as a modern day programming language. So here we've got that we can have a specifier qualifier be either another non-terminal for a type specifier or a type qualifier, where a type qualifier is simply one of the keywords to const and volatile, and the type specifier is one of our standard types that we have here, as well as it can be a struct or a union specifier or an enum or a type def. You will come across something like Backus Naur Form if you end up taking the course Compiler Design, because you'll have to look through your own eventual context-free grammar for the language that you define. So what I hope you got from this video was an understanding of what recursive and self-embedding rules in context-free grammars are, and how they're related but also some different, i.e. all self-embedding rules are recursive but not all recursive rules are self-embedding. And also what self-embedding means for a context-free grammar. And I also hope you've got an idea of the different ways in which people might be able to represent the same thing that we've represented for context-free grammars in using different syntax and things like that, and got a rough understanding of Backus Naur Form. If you want, you can go and look, for example, for extended Backus Naur Form, which is used much more commonly because it's a little bit more powerful. And maybe even look into some other ways in which context-free grammars can be expressed.